Hi all. We had already discussed substitution cipher, transposition ciphers, rota machines, steganography, and last simplified DES. So in this video, we can study DES, Data Encryption Standard. So it's a block cipher mechanism, or it's a block cipher algorithm, and it is the most common cryptographic algorithm, block cipher algorithm. So DES, Data Encryption Standard. It is otherwise known as DEA, that is Data Encryption Algorithm. Okay, it's a symmetric block cipher. Why it is known as symmetric? Because the same key is used in both encryption as well as decryption. That is why it is known as a symmetric cipher. Also, it's a block cipher. Why it is known as a block cipher? Because block by block encryption is used in this algorithm. Okay. So, Data Encryption Standard, DES, it is a symmetric block cipher. It is based on symmetric cryptography. Also, it's a block cipher mechanism. So, what are the parameters, or what are the inputs and outputs for this DES? We have two inputs for the DES algorithm. First one, plain text, and the second one, key. Plain text is 64-bit length and key is 56-bit length. And we will get a 64-bit output or cipher text. Okay. Data encryption standard is a symmetric block cipher. We have a 64-bit plain text, 56-bit key. Then output will be 64-bit cipher text. And it is developed in 1977 by NBS-NIST organization. Also, it's designed by IBM with input from NSA. Okay. So here there are two inputs. Which are they? One is a plain text and another one is a key. Plain text has 64-bit length and key has 56-bit length. So actually, this 64-bit plain text processing is done in three phases. First one, there is an initial permutation. And what do you mean by permutation? Permutation means based on the reordering, we can reorder the plain text. Okay, that is permutation. So we have first phase as initial permutation. After initial permutation, the second phase, it contains a 16 rounds plus a swapping mechanism. And the third one or third phase is inverse permutation. So, in DES architecture, we have three phases. First one is an initial permutation. Second one, 16 rounds plus a swapping. Third one, inverse permutation. So, for each round, there is a need of key. They are known as subkeys. 16 rounds are possible in DES structure. So for each round, there is a need of key. They are known as subkeys. Actually, the subkeys are coming from the original key. What is the original size of the key? It is 56-bit. Clear? From the 56-bit length key, we can derive 16 subkeys. Clear? And each subkey is used in each round. Okay. Then what is the length of the subkey? It is 48-bit. Clear? You can see in figure. So here two inputs, plain text and key, and the output is a cipher text. Plain text is 64-bit length, key is 56-bit length, and the processing of plain text with the help of this key is done in three phases. First one is an initial permutation, then 16 rounds plus a swapping. Third phase is an inverse permutation. Okay, there are 16 rounds and for each round there will be a subkey. These subkeys are generated from original key. Original key length is 56 bit but the subkey length is 48 bit. So we have a 16 rounds in DES. So we need a 16 subkeys from the original key. Clear? So this is the figure of DES encryption algorithm. So we have two inputs, right? Left side we can see a 64-bit plain text and right side we can see a 64-bit key. Originally we are taking 64 but after first permuted choice 1 permutations we get 56-bit key. So the key we used for processing is 56-bit. Okay. So key length is 56 itself. We are taking a 64-bit data. From that first permutation is over, we get 56. Actually that 56 bit is used for the actual processing of the plain text. Clear? That is why we already said the key length is 56 bit. So encryption, it is the conversion of 64-bit plain text into a 64-bit ciphertext. Okay. So first phase is an initial permutation, right? Then after initial permutations, you can see round 1 to round 16. 16 rounds are there plus a swapping mechanism. A 32-bit swap is there. Swapping is actually the interchanging of left half and right half. You have already studied the Feastel structure, right? Feastel structure. In Feastel structure, we can divide the original plain text into two. If it is a 64-bit plain text, we can divide it into 32-bit each. Okay. Then swapping, interchanging of the left half and the right half. That is, so 32-bit swap means. Clear? And after the second phase, we have a third phase, that is inverse initial permutation. Inverse of the initial permutation. Then we get a 64-bit ciphertext. Clear? That is the encryption procedure. Then for encrypting, we have keys. Subkeys are there. For each round, each subkey is used. So K1 to K16 represents the subkeys for each round. You can see in figure, size of the subkeys are 48-bit. Right. So they are getting from 56-bit key. So first you take the data, key data as 64-bit. First you perform a permuted choice 1 or permutation. Then you get a 56-bit. That 56-bit is used for the encryption procedure. So the key length in a DES data structure, DES algorithm is 56-bit. Clear? After getting 56-bit, first you perform a left circular shift. Okay. Then after that, permuted choice 1 or permutation 2, then produce a 48-bit. Again, after left circular shift, you again perform a left circular shift, then permuted choice 2 to produce next subkey, 48-bit. Clear? This will continue for each round. I think it's clear. That is, this is the figure of, or this is the structure of DES encryption algorithm. We have a 64-bit plain text and then it will produce a 64-bit ciphertext with 3 phases. First phase is an initial permutation, then 16 rounds plus swapping, then inverse initial permutation. For each round, there is a need of subkey K1 to K16. All are 48 bits. These 48-bit subkeys are generated from a 56-bit key. Originally, we are taking a 64-bit key, but after permutation, we get some 56-bit. Then, that 56-bit key is used for generating 48-bit keys. Clear? By using left circular shift and permutation. Okay. Next, how a single round of DES is working. So originally we are taking the plain text as 64-bit length, right? So first phase of a DES encryption is this 64-bit plain text is the input of initial permutation. That is we are performing a permutation over this 64-bit plain text, right? Okay. After permutations, we are getting a result. It's also a 64-bit. Then this 64-bit permuted output is the input of first round 1. Then how this round 1 working, or how this process of this round 1. So this is a single round of DES. So we have a 64-bit permuted output of the plain text. Then we can use a feastal structure here. We can divide that 64-bit into 2. Left 32 bits, Li minus 1, 32 bit, and Ri minus 1, it's also a 32 bit. Then we can perform some function in right half. You can see in figure. Ri minus 1 is connected with next stage, that is expansion bar permutation. Okay. You have 32 bits, you are expanded that bits, plus you can perform some permutation over that 32 bits, then produce 48 bit. You can see the length of the plain text, right half of the plain text. Originally it is 32 bit, you are expanded, then permuted, then produce a 48 bit length output. Clear? Then after getting 48 bit, you are performing an XOR operation with subkey Ki. So we have first input as 48 bit after expansion bar permutation, right? So we are performing a XOR operation. So there is a need of 48 bit key. Clear? That is why originally we are taking 56 bit key, but reduced into 48-bit subkey for performing this XOR operation. So for XOR operation, there are two inputs, 48-bit output of the expansion bar permutation function and the 48-bit subkey. Clear? After performing, we are getting a 48-bit output. Then it will be the input of next stage, that is substitution bar choice or S-box mechanism, substitution mechanism. Clear? So after S-box mechanism is a actually it is developed by Shannon, that is substitution bar permutation network. So first substitution mechanism, that is S-box. So after performing substitutions, we are getting 32. So 48-bit is reduced to 32-bit. Clear? Here in the substitution bar choice or S-box mechanism, we have 8 S-boxes are there. Actually this S-box is a matrix. Okay. So 8 S-boxes are there. For each S-box we have 6 inputs, but output is 4. Clear? 8 S-boxes are there. Each S-box has 6 inputs. So 8 into 6 is 48 for taking this 48-bit input. Clear? But the S-box, each S-box has 4 outputs. So 8 into 4 is 32. That is why the input of the substitution bar choice is 48-bit, but we are getting output as 32-bit. Why? 8 S-boxes are there. Each S-box has 6 inputs, but the output is 4. That is why it is taking 48-bit input, but the output is 32-bit. After we are getting a 32-bit output, again performing some permutation. So this substitution and permutation is actually the SPNet, that is Shannon network is the. After permutations, we are getting 32-bit. Then that 32-bit output is XOR with left half. You can see in figure. Then after performing XOR, we are getting an output as 32-bit. That is the right half of the next round. That is the right half of the next round, round 2. So what is the left half of this round 2? It is the right half of the round 1. Clear? So this is a single round encryption mechanism. Then how we are getting this subkey as 48-bit? So we have, originally we are taking 64-bit as key. Then after first permutation, permuted choice 1, we are getting 56-bit, right? Then this 56-bit is divided into two, 28 bits and 28 bits, performing left shift on both sides. Left shift, circular left shift is the, left shift is the. Then after performing left shift, we are performing some permutation by contraction. So 56-bit is reordered or permuted, then contracted, that is then reduced that size into 48-bit. Clear? That is the first subkey for the first round. Next, we can generate next subkey. From where? That is after performing left shift on both sides, left half and right half. Again, we are performing left shift and right shift. Then generating subkeys by using the same procedure as in the first round. Clear? So this is a single round of DES mechanism. So here 64 plain text is divided into two halves. Right input is first expanded 48 bits using permutation and expansion, resulting output XOR with 48-bit subkey, and the resulting 48-bit passes through the substitution box, produce 32-bit, then permute 32-bit, produced result XOR with left half and produce right 32-bit of the next round. Left half of the next round is the right half of the previous round or previous result. Clear? So this is the explanations of DES encryption. Then 56-bit key is divided into two halves, perform left shift, then combine the result and perform permutation by contraction to produce a 48-bit key. So the input is 64-bit plain text and 56-bit key. We are producing a 48-bit subkeys for each round. We have an initial permutation, then 16 rounds plus overlapping, then inverse permutations. Clear? So for 16 rounds, we have 16 subkeys. This is the initial permutation and inverse initial permutation matrix. You don't study this for exam. You just understand this is the initial permutation and inverse initial permutation matrix. And this is expansion by permutation and permutation function matrix. Clear? And this is the S-box structure. So we have right half as R as 32 bits, then expanded into 48 bits, performing XOR with key, then that output will be the input of substitution bar choice or the input of S boxes. How many S boxes are there? 8 S boxes are there, S1 to S8. You can see in figure, each S boxes have 6 inputs and 4 outputs. Okay. So total 48 inputs. That's why they are accepting 48-bit input. Okay. But it produces only 32-bit. So this is the structure of S boxes. Clear? Next so this is the explanation of DES structure and what is Avalanche effect in DES algorithm. So Avalanche effect means if there is a small change in the input, it will produce a large change in the output. That is, if we are changing a bit in a plain text or a bit in a key, it will produce a large change in the cipher text. That effect is known as, or that property is known as avalanche effect. You can see in this example, we have two plain text 1 and plain text C. You can see only one bit is differ in this plain text. That is, in plain text 1, first bit is 0, but in the plain text 2, first bit is 1. Okay, but in ciphertext, if we are encrypting this plain text 1 and plain text 2, and in the ciphertext you get the difference as 32-bit difference is there. So a small change in the input, it will make a large change in the output, means it's an avalanche effect. That avalanche effect is found in this DES structure. Also, you can see there are two keys are there. Only one bit difference is there, but the ciphertext difference means it's a 30 bits difference is there in the DES. So this is the avalanche effect. Now, what are the strengths of the DES? Actually, there are three main strengths. It uses a 56-bit key. So there are 2 raised to 56 possible keys are there. So it will make the DES as strong. And the nature of DES algorithm, we are using S boxes for the substitution mechanism, but the design of S boxes were not made public, so that's why the security or the strength of the DES is more, and also it is resistant to timing attack. So these are the three strengths for the DES algorithm. Okay, thank you.